Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 19 of this course on machine learning for art system science. We are in module 3, which is where we are using machine learning for discovering new insights related to the art system. So, in the topic of this lecture is going to be identifying causal relations from time series. So, this topic we will cover in 2 lectures. This is the first of those 2. So, the topic of causality we have discussed briefly in module 1. In this lectures we are going to see some concrete use cases. The concepts we are going to cover in this lecture are, first of all, we will recapitulate the different causality questions in art sciences and the issues we face while solving them. Secondly, we will see some applications of Granger causality and causal hypothesis testing, and then we will also see spatiotemporal Granger causality for attribution. So, here is some the broad questions which are related to causality in art system sciences. We had briefly touched over this in one of the lectures of module 1. Today we will see in this lecture and in the following lecture we will see some use cases of each of them. So, the first type of use case is causal hypothesis testing. This is here we may make certain kinds of hypothesis regarding a cause effect relation between, let us say, different art scientific or geoscientific phenomena in different parts of the world. So, climate scientists or art scientists have various understandings or various notions about which event or which kind of variable influences which other variable and so on, but these are mostly hypotheses. For example, it is known from empirical data that the El Nino southern oscillation, which happens in the central Pacific Ocean, has a bearing on rainfall in India, monsoon rainfall in India. So, one hypothesis there is that the El Nino or that ENSO phenomena is a cause and the Indian monsoon is the effect. But how far is this true? I mean, correlation is there, but as we have discussed earlier also, correlation and causation are not the same. So, here the hypothesis is that one is the cause and the other is the effect, but it could also be that it is the Indian monsoon which is the cause and the El Nino southern oscillation is the effect, or it could even be that there is a bidirectional relation, or it might even be that neither of these is the cause or the effect, but there is some confounder which is the common cause of all of these. So, which of these possibilities is true? So, here we can make a hypothesis. Now, we need to test the hypothesis. So, you might be familiar with the idea of hypothesis testing, which is an important question in the domain of statistics. So, we know that we start with a null hypothesis and we define some test statistic and we define some criteria by which according to which the test statistic, I mean the null hypothesis can either be accepted or rejected at a certain level of confidence and so on. So, that kind of hypothesis testing related to causality is something is a question that frequently pops up in this domain, but then again there are sub questions like what should the test statistic be, or how exactly we can evaluate the or test the hypothesis, etc. So, these are that will depend on the exact context in which the question is being asked. The second set of problems is developing something like a causal network all over the world. So, climate networks and so on, the networks based on correlations, then networks based on event synchronization, etc., we have discussed earlier. So, where we look upon the whole earth surface as something as a graph and every location or every grid as a node, and we put edges in between them. Now that kind of a network can be a causal network, where we can like draw an edge from a node u to node v, if we can be sure that node u is the cause, node u or a particular variable at node u is the cause of another variable at node v. So that like that way we can develop some kind of a causal network. Of course, that will require us to do the causal analysis and identify lots of cause effect pairs in different parts of the world. So one of the important or like one of the most ambitious research questions in this domain is to build some kind of a causal complex network of the world that will like enable us especially to understand the phenomena of teleconnections, in which like one phenomena in one part of the world is known to be the resulting in another phenomena in another part of the world, but then for that kind of relation to be understood in the cause effect scenario, we need to understand the mechanism, the exact physical mechanism in which one of them influences the other. So that kind of thing can be achieved if we can build something like a causal complex network of the world. Then another important set of problems is that of attribution, and especially the attributions of extreme events. Say for example, like a heavy rainfall event happened or a cyclone happened in some region, then can we attribute that thing to like a larger phenomena like say climate change or something like that, or can we say that had climate change not happened, had we like been at the same climate as let us say 200 years earlier, then this particular event would not have happened. So that is in general a very difficult question to answer, because for that we need the counterfactual scenario. What if there was no climate change? But then we of course we do not know that, because we have only one version of the reality. We do not know any other version of the reality in which there is no climate change. So then how to answer these questions? So this is the attribution problem, which allows us or which aims to actually estimate what would have happened in counterfactual scenarios. So since we do not have the counterfactual scenario, we have to somehow estimate its statistics based on whatever data we have available, and then see if a particular event of interest which actually happened, we have to try to estimate whether it could have happened in the counterfactual scenario also. So this kind of analysis, this is known as the attribution causes. The second one is the fourth one is that of model evaluation. So we know that or we have already discussed several times earlier in the previous lectures that there are these process models which are which aim to simulate various earth system processes, and like there might be hydrological models, there might be climate models, there might be ocean flow models, seismic models, and so on. Now the question is how realistic are those models? That is like suppose there is indeed a causal relation from one variable to another in reality, that is we know that like geoscientific variable A influence at location S influences geoscientific variable B at location S prime. Then is that kind of a causal relation, is it preserved in the model simulations, or or there is merely some kind of simple correlation between the two? This is important because like these models, these are used to evaluate the various counterfactual scenarios which we just discussed. That is, one possibility of evaluating a counterfactual scenario is to simulate it using the models. But if the models they are not able to capture these causal relationships, then the simulation of these counterfactual scenarios, that will be futile, because we will not know whether a particular event which we are interested in would have happened in the counterfactual scenario or not, because we do not know, because the model is not able to understand its causes. So, that it is whenever we build a simulation model, a process simulation model, it is very important to make sure that it is able to preserve all the causal relationships that are present in reality. So, this is one important criteria according to which these models may be evaluated. Now let us discuss some of the challenges that we face when we are applying causal analysis in the earth system sciences. So, these we had discussed briefly in another episode in module 1. Let us discuss this in a bit greater detail now. So, the first challenge is autocorrelation. So, we know that autocorrelation is when basically the values of one variable depends on the past values of the same variable. So, if you remember, the notion of Granger causality is aimed to express z at time t as a function of z of t minus 1, z of t minus 2, etc., along with the potential cause, which we may call as W. So, we can in Granger causality we try to express z in the present value of z in terms of the past values of z as well as the past values of the potential causal variable. Now, if the autocorrelation is so strong, that is, if the coefficients of the past values of z tend to dominate the coefficients of the past values of the causal variable W, then even even if some causal effect is there, the autocorrelation may be so strong that it cannot be separately discerned from the autocorrelation. So, that is the presence of strong autocorrelation in the time series hampers the causal analysis. Then there is a question of time delays or time lag. So, we have earlier also discussed that especially when there is some kind of a teleconnection relation, say for example, these two phenomena which are happening in different parts of the world, which are quite far apart. So, typically there is a time delay between any event that happens here and another event that happens here. It might be difficult to understand how much time delay it is, and if the time delay is quite long, then it is possible that in whatever causal analysis we are doing, the time delay will actually be beyond the window or beyond the time window which we are considering, so that the delayed effect will simply not be captured. Then there are nonlinear dependencies. So, in case of Granger causality, we had discussed that we try to express the future values of a variable in terms of the past values or as a linear function of the past values. So, we fit some kind of a regression model, but the relation can be nonlinear also. Now, as I said, the scientists are currently trying to solve this issue by using nonlinear Granger causality. Then comes the question of chaotic state dependence. So, especially a chaotic time series is notoriously difficult to predict, because the nature of chaos is such that if there is some small deviation at any point of time, the future values may take a completely different trajectory. So, in the presence of such chaos, identifying causal impacts becomes very difficult. It might also happen that the different phenomena which we are studying happen at different time scales, that is, one may be fast and another may be slow. So, if that is the case, then again identifying the the causal impacts might become very difficult, because the causal variable that might be very slow moving, and the observed variable or the effect variable that might be fast moving. So, we will find it very difficult to express one time the impact of one time series on the other. Apart from that, there are also some challenges which arise out of the data. Say for example, in case of there might be unobserved variables, so these are basically the confounders which we talked about. So, remember the example of shark attacks and ice cream sales. In that case, there was an unobserved variable, the temperature. Now, similarly, when we are trying to express one or try to understand the causality relation between two variables, it is possible that both of them are impacted by a third variable which we have not taken into account, which we are not aware of. So, in the or it may also be that that variable we may be aware of, but we have no way of measuring it. So, the presence of such unobserved variables makes the job even more difficult. Then there are other issues like time subsampling and so on. This is related to the problem of different time scales. So, like we of course cannot measure that entire time series. We have to, like any sensing device, it will measure a particular variable at fixed intervals. Now, it might happen that the process is so fast that changes take place within that within that interval, or rather its the impact might be at a higher resolution than what we can sample at. So, if that happens, then we may not be able to identify the relations, or we may identify it as incorrectly. That is, say for example, there might be a lagged relation like this, but we may end up interpreting it as some kind of a contemporaneous relation. Then there are of course problems related to measurement errors, that is when we fail to measure the variables accurately, and thereby we may end up coming up with relations that are spurious. Then there can be selection bias, where we focus only on one part of the data which is not representative of the entire data. If the data is discrete, then it becomes even more harder to, because if you have observed the Granger causality and such models, they are all continuous valued distributions, but in case we are dealing with discrete data, it becomes a more complicated situation. And then there are other kinds of uncertainties related to dating of the variables, and other computational issues like the sample size, the dimensionality, the uncertainty, and so on. So, now let us come to a few use cases. So, in the rest of this lecture and in the following lecture also, we will see some use cases of causality in earth sciences. The first one is based on Granger causality of time series. So, here the task is to explore the Granger causality between global average observed time series of carbon dioxide and temperature. So, so it is generally known that carbon dioxide emissions has a role behind global warming, that is the general rise in the global temperature, but can we try to quantify it? So, the detection and attribution methodologies have been developed over the years to delineate anthropogenic from natural drivers of climate change and impacts. Anthropogenic means the human induced. A majority of prior attribution studies which have used climate model simulations and observations or reanalysis datasets have found evidence for human induced climate change. This paper tests the hypothesis that Granger causality can be extracted from the bivariate series of globally averaged land surface temperature observations and observed CO2 in the atmosphere using a reverse cumulative Granger causality test. This proposed extension of the classic Granger causality test is better suited to handle the multi-source nature of the data and provides further statistical rigor. The results from this modified test show evidence for Granger causality from a proxy of total radiative forcings, which in this case is a transformation of atmospheric CO2 to global temperature. Prior literature failed to extract these results via the standard Granger causality test. A forecasting test shows that a holdout set of the global temperature can be better predicted with the addition of lagged radiative forcing as a predictor, lending further credibility to the Granger test results. However, since second order differenced RC is neither normally distributed nor variance stationary, caution should be exercised in the interpretation of our results. So basically the whole idea is that they have two main variables, the global temperature and CO2, and they are and they are relating it to another variable called the total radiative forcing, which they denote by RC here. So so whenever we try to fit a Granger causality relations, that is, we try to express one variable in terms of the other using a linear relation, we are basically making a hypothesis, and that's a hypothesis which we need to test using the data which we have had. So it's basically a testing of hypothesis problem, where we need to define a test statistic, and then either and we have a null hypothesis, and we either accept or reject the null hypothesis at certain level of confidence. So in this paper basically they the null hypothesis is that one of the so first of all, these are some of the predictor variables. So this is the thing which they are trying to predict, the global land surface temperature anomaly. So as you can see, it has it is steadily rising up like this, which indicates the global warming. So this is a variable which they are trying to predict, or is the effect variable for which they are looking for causes. So one possible cause is the CO2 emission, which also is increasing like this, and they find that it is some kind of a proxy for radiative forcing, which also, as you can see, its plot looks pretty much similar, although the units are different. And then there is something known as the ENSO anomaly index. So this is like a phenomena in the Pacific Ocean, which which can be understood as some kind of a proxy for warming. And so they come up with these plots. As you can see, d equal to 2 means like a time lag of 2 time units. So here they are plotting this bivariate plot of radiative forcing and the global temperature, and this is what the plot looks like. So when we go for Granger causality, we will try to fix some kind of a linear relation between the two, but as you can see that it does not seem to be that great an idea to represent this kind of data with a with a linear relation. Similarly, this is here they make another bivariate plot with what is known as a robust trend. So this is the hypothesis of Granger causality, where there are two variables y and x. So let us say that x is the global temperature, the thing which the so called the effect, and y is the cause, which may be the CO2 emissions and so on. So the Granger causality relation is to express one the present value of each one of them in term as a linear combination of the past values of both of the others, and then see if these components, the components of the other one, in this case the betas and the omegas, if they should be 0 or non-zero. Okay. And so these are here for the to understand what should be the proper lag, because as we had discussed earlier, these effects cannot be instantaneous. It is not that if there is an emission this year, immediately the same year the temperature will also go up. In fact, we can expect some kind of a lag relation, but how much should that lag be? So they use the help or that what is known as the Pearson correlation coefficient, and they actually measure the Pearson correlation coefficient between different pairs of variables, like the global temperature and RC meaning the radiative forcing, and this means the is something like the second derivative. They have so we have the original time series, then we can take the time the time derivative of it by doing first order differentiation. That is we have let us say we have a time series of x, we will x, instead of xt we will have xt minus 1, and instead of xt minus 1 we will have xt minus 1 minus xt minus 2, and so on. So and this so that is the first order differencing. Then similarly we can have the second order differencing also. So like we have so these things are done basically to get rid of the local oscillations and so on, or to get rid of the local what is known as the noisy components, and to make the series a bit smooth. So after smoothening the series by this differentiate by two second degree differentiation, they carry out the Pearson correlation test of the at different time windows between the between the different pairs of variables, and they see that say around 1991. So the p value between GT2 and RC2 is like very high, it's like almost close to 1, while there are other periods of time when they like their correlation coefficient was effectively nil. So like this shows how the Pearson correlation coefficient between the two things or between the different pairs of things, they vary, and as we can see that for the same pair of quantities there might be periods when they are strongly correlated and there might be periods when they are not strongly correlated. So accordingly they try to come up with this kind of time varying testing of the hypothesis at different points of time or at different windows. They carry out the testing of the hypothesis using a suitable p value and see at which time or which intervals of time the p value is high enough, that is the causal relation can be validated, and in which periods it does not hold. So accordingly they come up with their conclusions. And then here is another paper. This is also based on Granger causality, but here the aim is slightly different. Here the aim is to carry out spatiotemporal causal modeling for climate change attribution. Here, unlike the previous works where we talked about the network, here again we have a graph, but the difference here is that the nodes here stand for the different variables, not locations but variables, and we try to come up with a network structure like where there is a particular variable of interest which we call as this TMP, the temperature, and so the aim here is to so once again the aim is to attribute the warming, that is the rise in global temperature, and we are trying to see which of the different factors like impact this global temperature more. So so once again they take help of Granger causality with a catch. In this case the target variable, the temperature, that is like again spatiotemporal. Let's say we are measuring it at a location S and a time t. So when we are looking for predictors, we will have the following condition on the predictor, that we will look only in the vicinity, that is for if the like in case of the target variable, if the location is S and time is t, then its predictors we will search like in a small neighborhood of the location S and within a short time window t, like t minus L. And so for that purpose they define some kind of a special penalty and a special penalty function, which means that if the if any predictor is far away, like is located at a position which is far away from the target variable, like it will be some kind of penalized. So I mean it can be accepted as a predictor, but with a penalty term. So the idea is that I do not want predictors which are very far apart, I want predictors which are close by. So that kind of thing is ensured with the help of this special penalty function. Apart from that, we also have a sparsity penalty function. This is the usual sparsity function which the sparsity condition which we have in case of sparse regression, where we do not want too many predictors, we only want the most critical predictors, that is the variable selection problem. And so accordingly they have this kind of a linear relation which they carry like the linear regression, we can call it as a regularized linear regression, which they carry out and they get the final answer. And these are the output of the regression. So here as you can see, like when it is very sparse, that is when the sparsity is very high, then there is only one edge in the network which shows that the H2, the hydrogen concentration, seems to be the strongest driver of the temperature. Then if we relax it a little bit, then CO2 becomes the next largest driver. Then as we reduce the sparsity a little bit, then all these things including the carbon monoxide, etc., these become the predictors, and so on. And gradually, as we keep on relaxing the sparsity, we see more and more drivers being added. But the catch is that, like when the sparsity is very low, then we get only the most crucial drivers, and those seem to be the hydrogen, carbon dioxide, etc. So basically the Granger causality also has some limitations, namely that it is unable to identify the confounder effects. It does not work well in the presence of autocorrelation and contemporaneous relations, and so the alternative to Granger causality is to use conditional independent based approaches, which we will see in the next lecture. So these are the reference for the two papers that we discussed, and so applications of causality in earth system science may face many issues such as autocorrelations, lags, unknown confounders, timescale variations, etc. Granger causality can be used to check if one time series can be predicted using another, and regularization functions can be used to promote variable like variable selection under different criteria. They can be used for Granger causality. So that brings us to the end of this lecture, where we will discuss more on the causality in the following lecture. Till then, goodbye.